Okay, good morning. Let's continue with our topic of discussion, which is the phasors and complex impedances. So chapter 5, and this is where we stopped, right? This is where we stopped on Wednesday, and we had just gotten into the representation of the phasor. So again, as a recap, phasor is a vector in the complex plane. It is a single snapshot representation of a time-varying sinusoidal waveform. So time-varying sinusoidal waveform looks like this, has a positive and a negative peak, plus Vm minus Vm, and we represent it as one rotating vector in the complex plane. It's a single snapshot. It doesn't contain any frequency information. Okay? It does have omega, of course, but the description of the vector only requires two things. It requires the length and the angle it makes with the real axis. And that is provided by the magnitude or the peak value of the waveform and the phase or the phase shift of that waveform. So you have Vm and you have theta. And you can write the phasor directly, Vm with the angle theta. Okay, that gives us the vector in polar coordinates. We can represent current also in the same way. And I'm going to put little studs at the end, and that would be magnitude of the current, the phase angle of that current. So phasor for V, phasor for voltage, would have magnitude Vm, phase angle theta, and same thing with current. So voltages and currents are represented using phasors, and then we will look at impedances. Okay. So one notation about this is that we are representing only one full cycle. Okay, one full cycle. Now, x-axis is of course always time. Y-axis could be either voltage or current. In terms of radians, one full circle is 2 pi, right? 2 pi. This case is the way I like to make a poor joke, which is like a pie of pizza or a pie, desert pie is 2. Twice, right? Circle is 2 pi. So when you take the entire full cycle, which is one full cycle, and we represent it as one circle, in radians, this comes out to be 2 pi. So one time period is equivalent to 2 pi, or 360 degrees. Right, 360 degrees. One half cycle is 180. So pi, or 180 degrees. And a quarter cycle would be pi by 2, or 90 degrees. So in radians or in degrees. But as I said, our time domain expression, we keep the phase shift separate in degrees. For mathematical purposes, we want to describe, well, there's also other reasons, but primarily for this class, for mathematical purposes, we want to describe the time varying signal, the time domain signal as a rotating vector. And for that, we need the angle. Okay. So pause and let me know if you have any questions. All right. There is one other important thing to keep in mind. This is known as a phasor transform. We are transforming a time domain expression into the frequency domain. So there is a derivation that's known as the phasor transform. But simply looking at the vector, we can see it forms a right angle triangle, right? So trigonometric identities and all. There is a resulting, not a resulting, but a condition that must be met. In order to perform this transform, the time domain expression must be in cosine, not in sine. Okay, the time domain expression must be in cosine. You cannot transform if it's in sine. You have to transform the sine to cos x, sine x to cos x, and then you can write the phasor transform. And hence, I had that equation in the previous slides. Where'd it go? There it is. Sine x is cos of x minus 90. Okay, so if the expression is in sine, you convert it into cosine first, and then you do the phasor transform. Sine x is equal to cos of x minus 90. Again, it's the two angles, the side, it's a right angle triangle, right? It's a right angle triangle. So the far end of the vector forms a 90 degrees here. So the sum of these two angles is equal to 90. That's where it comes from. Okay. So that was for the sources. Let's look at impedance. Okay. So first thing I would say or state about impedance is that think of it as being synonymous with resistance. Just look at the English language words, okay? We have resist, impede. Basically, both are signifying opposition to something. Like resistance in electrical engineering or in physics is basically the opposition to the actual flow of current. Okay, so that is resistance. Then we introduce a new term called reactance. And reactance is associated with energy storage. Okay. So what is reactance? Let's talk about reactance. For an inductor and for a capacitor, we know if you apply a current or a voltage, it sets up a magnetic field or an electric field that stores energy. This stored energy will oppose any change in the input. For an inductor, if you apply a current, that current delivers energy, it's stored in the magnetic field. That magnetic field is going to oppose any change in that input current. That change is not to oppose the flow of current, but it opposes any change in the value of that current. And that is manifested and stated as reactance. Same thing with a capacitor. Capacitor, you apply voltage. That voltage is it transferring energy. It is stored in an electric field. That electric field will oppose any change in the input voltage. It is not going to oppose the current flow or the charge buildup, but it's going to oppose any change in that input. Okay, so it's not a direct opposition. Hence, it is not resistance. We have a new term for it because it's a different phenomenon. It's a different phenomena than a resistor or a resistance. So we call it reactance. Okay. So reactance is associated only with inductors and capacitors, only with energy storage components, not with resistors. And resistance is purely associated with resistors. And that's it. Okay. So only for resistors. Actually, I wrote it the other way around. Resistance is solely with resistance. A reactance is associated only with inductors and capacitors. Okay. Only with inductors and capacitors. Now, how do we mathematically represent reactance? Well, we use complex numbers. Okay, we use complex numbers. Again, there are some derivations for this too. When an inductor receives the current, right, it sets up the voltage, it sets up the magnetic field, you see a voltage across it. That magnetic field gives rise to an opposing voltage. That opposing voltage opposes any change in the input current. So the voltage could change first. The voltage is measured across the inductor, but the current changes after. And for an inductor, there is a phase difference. There is a phase difference between the voltage and current for an inductor. Okay, if this represents VL, voltage for the inductor, then the current is 90 degrees behind. This would be IL. You don't have to draw these out. Okay, this is for explanation purposes. Again, there is a difference between the voltage of an inductor and the current of an inductor. In this case, the current is behind or lags the voltage. Okay, the current is behind the voltage or lags the voltage, or you could say voltage is ahead or voltage leads the current for an inductor. Okay, and the result of that is there's a phase shift between the voltage and current for that specific component, meaning that specific inductor. Always 90 degrees, plus 90, always. Okay. And the opposite happens for a capacitor. Capacitor, we apply a voltage and it opposes any change in that input voltage. So the current could be measured. Current that's flowing in the circuit around the capacitor can be measured, but the voltage would be slower to change. So the voltage always lags in a capacitor. So in a capacitor, the waveforms are flipped. In a capacitor, the current waveform IC is ahead of the voltage. This would be VC. So in this case, again, remember, the right side is positive numbers, it's in the future. So if it's on the right, it's behind. If it's on the left, it's in front. So here, I would say IL lags and VL leads. And here, VC lags and IC leads. Okay. So for a capacitor, theta VC minus theta IC is equal to minus 90 degrees, always. This would be plus 90. In capacitor, it's always minus 90. Okay. Now, the mathematical representation. Remember what I said. We are going to use complex math to make our math less complex. We don't want to solve differential equations unless we really have to. So phasors, we represented using complex number. Phasors are the complex number representation of your sources. Voltages and currents are both replaced as phasors using complex numbers. For impedance, reactance, and resistance, we use complex numbers, and we introduce a new term, impedance. And impedance is a complex quantity, mathematically speaking. It's a complex quantity given by R plus JX. Where R is the pure resistance, X is the reactance. Okay, R plus JX. Capacitors and inductors do not have resistance. We are talking about ideal inductors and ideal capacitors. They do not have resistance. They only have reactance. Remember, they do not oppose the flow of current, not directly. They oppose any change in the current or voltage. So that is mathematically represented with reactance. Because you're using complex numbers, the reactance is represented using the imaginary number. In electrical engineering, the imaginary number is J. So if you read a book or you take any other class, you might hear the words or the phrase imaginary reactance. That reactance is not a figment of anyone's imagination. If you read the words imaginary reactance, it's simply talking about the mathematical representation of reactance. I want to be absolutely clear and make sure every student understands. If you read the words or hear the words imaginary reactance, it is talking about the mathematical representation, it's not a figment of somebody's creation, okay? Not a figment of somebody's imagination. So you would often hear the terms imaginary reactance. It's mathematical representation, but reactance is a real physical phenomenon. Okay, it has a basis, it has a physical basis in real life. Okay, it's just a mathematical representation. We write the equation R plus JX. So impedance is noted by uppercase Z, resistance, as you know, it's uppercase R, reactance is uppercase X. These are polar coordinates or Cartesian, R plus JX. If you transform it into polar coordinates, sorry, rectangular coordinates, not polar, rectangular coordinates. So this is rectangular, this is polar coordinates. You can transform these into a vector. Now this vector is not rotating, okay? It's just a vector. It's a vector in the complex plane. You have the real axis, the imaginary axis. You have the real part of the impedance on the real axis. You have the imaginary part, reactance on the y-axis. And the combination of both, the hypotenuse or the third side of the triangle, gives you the magnitude of the impedance. And the angle it makes with the real axis gives you theta. Okay, so magnitude Z, phase angle theta. This is important. Why? It's because as I was saying, ZL does not have any resistance. So it's 0 plus JXL, JXL. Okay. That simply means impedance of an inductor is J times the reactance, imaginary reactance. Similarly for ZC, it is 0 plus, actually it's not plus, but it's minus. And I'll explain why it's minus. For now, just leave it as plus. And then you can say it's JXC. Okay, JXC. So it's a complex quantity, JXL, JXC. There is no such thing as the impedance of a resistor. Okay, a resistor behaves exactly the same way it does for AC and for DC. So there is no such thing as impedance because it does not impede anything. It resists the flow of current. It does not have a field or magnetic or electric field to change, to oppose any change in the input quantity. So it does not impede anything. It has resistance. It does not have impedance. And so ZR is simply R because it will be R plus J0, which would be R. So let's take a pause, think on it. Let me know if you have any questions. Again, this is one of the most important talks for the rest of the quarter. So I want to make sure everybody understands. And mostly it's just math. Okay. Yes. No, impedance is just a mathematical quantity that combines both resistance, and reactance. The question being asked is what's the difference between impedance and reactance? In some cases, it would be one and the same, because for ideal inductors and ideal capacitors, there is no resistance. So the reactance is the impedance.
So does that mean like that reactance actually has like a physical quantity?
Mhm.
It resists change. D does not have an actual physical.
Well, well, Z would uh, encompass reactance, and so in that case, sorry about that. So we can say impedance is the reactance. The reactance is not even used outside of like technical talks or technical books and stuff. Mostly, it's always impedance. So as an example, again, I'll go back to the audio engineering or audio devices, consumer devices. If you pick up any speaker separate, well, actually, whether it's a home theater in a box or a separate speaker or a separate amplifier, if you look at the spec sheet, at the back, it will say 8 ohm impedance or 6 ohms impedance. Why? Because the speaker has a coil around a magnet. Any kind of speaker has a coil, which is an inductor around a magnet. That coil is an inductor. It has reactance. It has impedance. It will not say reactance. It will simply state impedance. So if you pick up a pair of headphones, pick up a pair of any kind of speakers, go online, download the spec sheet, and you'll always read the words impedance. So in real life or in everyday life, we simply use the words impedance. And as I stated at the beginning, we can kind of think all of them as synonymous to each other. And which brings me to my next point, that the symbol for all three is exactly the same. Same as the zigzag lines for a resistor. The units are also the same. I talk about reactance because it's the explanation for how we deal with impedance. But going forward, we'll always talk about impedances. Okay, we represent all three quantities with their equivalent impedances. So inductors and capacitors are replaced with the impedances, resistors are replaced with their impedances, but the impedance for a resistor is just R. Whereas for inductor and capacitor, we do replace it with its impedance. Okay, any other questions? So the equation for that comes from the frequency, omega L and omega C. Omega is 2 pi f. Omega is the angular frequency or angular velocity in radians per second, how fast it is rotating in that complex plane, right? In terms of hertz, omega is 2 pi f. So omega is 2 pi f. So here it's radians per second, it's pi, and frequency in hertz. Hertz, of course, is the number of cycles per second, right? Number of cycles per second. So we can write XL. XL is omega L or 2 pi FL. XC is 1 over omega C or 1 over 2 pi FC. 2 pi F times the inductor value, 2 pi F times the capacitor value. Okay. So if impedance is synonymous with resistance, impedance is a complex quantity. Phasors for voltage and phasors for current are also complex quantities. we can apply all of our equations that we learned in chapters 1 and 2 exactly the same way as they are by transforming all into a complex quantity. So instead of solving differential equations, derivations, integrals, we can apply Ohm's law as it is, KVL, KCL, all our analysis techniques, everything exactly the way it is, except the math is now uses complex numbers. Hence, my insistence on the students to use the complex number worksheet, because if you cannot do your complex math on your own calculator devices, you will not be able to do anything else in that class, in the rest of the class. Okay. So again, if you haven't yet taken a look, download the worksheet, practice, become an expert in using complex numbers on your own devices. Okay, so let's see. This is going to be important. The phase difference between a capacitor and an inductor. Okay, if you take any inductor, the phase difference between its voltage and its current, it's always plus 90. For a capacitor, it's always minus 90. There's a mnemonic that will help you remember that. That's Eli, Iceman. It's named after Eli Manning. You want to know who that is? He was the quarterback for the New York Giants. Not really. This just came about. What does L stand for? Inductor. C, capacitor. I, current. Current. E, wild guess. What does E stand for? EMF, electromotive force, or other word for voltage. So for an inductor, the voltage is ahead of the current. For a capacitor, the current is ahead of the voltage. Okay, Eli the Iceman. When it's ahead, meaning voltage minus current gives you plus 90. There, voltage minus current gives you minus 90. The reason we are doing voltage minus current is because of Ohm's law. So let's go here. Ohm's law, V equals I times Z. V equals IR, R is replaced with the impedance Z. So if you apply Ohm's law to any component, the impedance and the current, the product of the impedance of that component and the current flowing through it should give you the voltage across that component. No need to solve differential equations or derivations. You get my drift here? Chapter 3. Voltage for an inductor, VL is L di over dt. The reverse is the integral of the current, right? If you wish to find voltage, you take the derivative of the current. If you wish to find the current, you integrate the voltage. You perform derivation and integration for that inductor. Instead of doing that, you simply use complex numbers and you apply Ohm's law. Does everyone get what I'm saying? Hopefully. And so from Ohm's law, I can state Z is V over I. V over I. Now, if all of these are complex quantities, what do we have? We have magnitude of Z, and the phase angle of Z would give you magnitude of V divided by magnitude of I, and this would be phase angle of the voltage divided by the phase angle of the current. We will go into the math in a separate slide, but for now, I want to just, if you know this, that's great. If you don't, I'll let you know right now. When you divide phase angles, it gets subtracted, meaning theta V divided by theta I becomes theta V minus theta I. That's how you would perform that math. Okay. If you're dividing two phase angles, the mathematical result is theta V minus theta I. Okay. It's the angle it's the angle that it makes with the real axis. So it's always the impedance angle, theta Z, is always voltage minus current. And if it's always voltage minus current, and you go back to this slide, voltage minus current for an inductor is always plus 90. Voltage minus current for a inductor is always, for a capacitor is always minus 90. So the impedance for a inductor is always positive. For any specific inductor, the phase angle will always be plus 90 degrees. Doesn't matter what its voltage is, doesn't matter what its current is, doesn't really matter what levels they are, but the phase angles between them will always be plus 90. And ZC, for that reason, will always have the angle of minus 90. Always. Going back to chapter 3, I began my talk for chapter 3 and introduced capacitors and inductors by saying they are very similar components, but in many respects, they are completely opposites of each other. This is the moment I would remind you of that. And this is going to be very useful in real life applications. So again, impedance for an inductor is always plus 90. Impedance for a capacitor is always minus 90. Okay. Ohm's law for a resistor simply applies V is I times R, right? V is I times R. Then instead of solving differential equations or derivatives and integrals, you can simply find inductor voltage as IL times ZL, VC as IC times ZC. Okay. KVL and KCL also work exactly the same way that we did in chapters 1 and 2. The only difference is they are now vectors. And so they're complex quantities. You're using complex numbers. You have to take phase angles into account. And I will come back to that just a second. So you have to take phase angles into account. Let's say, and I'll use an illustration example. Let's say you have a DC circuit, right? As an example, DC voltage of, let's say, 10 volts applied to a series network of resistors. You don't have to draw anything out. Let's say this is 5, this is 3, and this is 2 volts. 2 ohms. 10 volts being applied to 10 ohms. Straight up, you have plus 5 volts, plus 3 volts, and plus 2 volts, right? 5, 3, and 2. If you were to graphically plot these voltages, how would you do it? You would start at 0, 0. The x-axis, we'll take the x-axis and plot the voltage. Let's say we use current and voltage as a reference. So then we start at 0, 0, we plot the first voltage. 5 volts. Let's say that these were vectors, right? But they don't have any phase angle, so they're lying flat on the x-axis. So now we have 5 volts vector lying flat on the x-axis. Where would you plot the second one? From the end of the first one, right? Because we're adding them up. You have to add everything up. So from the end of the second one, we have to plot. So from the end of the first one, we plot the second one. And then finally, we plot the third one from the end, the second one. And then this gives you 10 volts, the sum of that. Make sense? Easy enough? But now you have vectors. You have vectors, right? So if this was AC applied voltage and instead of resistors, they were like impedances, like inductors or capacitors, then you'd have to take the phase angles into account. So let's say you had an AC circuit. So this is DC, this is AC. You start at 0, 0. Let's say you might have something like this, 5 volts for a resistor perhaps. Then you have to take the phase angle into account. Magnitudes alone will not add up to KVL. Again, these are complex numbers. So oftentimes students say, oh, I took measurements in the lab, but when I add them up, it doesn't make sense. Well, it doesn't, because we're only measuring magnitude. We are not measuring the phase angle. Okay, so we have to calculate the phase angles. And so when you add something like this up, this, should give you the total VS that you're applying. And this is what you're doing in the lab for next week. You're going to take AC measurements, and then you're going to plot a phasor diagram where you will verify KVL. Okay. And then, of course, if you have a capacitor, again, you plot it, you introduce the capacitor in there, and you take all the phase angles into account. And when you join from the start point to the end point, that would verify your source voltage. So KVL works, KCL works, everything works, except it's all in complex numbers. Okay, everything is in complex numbers. All right, let's take a pause. Let me know if you have any questions. Any questions at all? None? Yes. No, not necessarily. And what do you mean higher? I mean, I could apply 5 volts DC and 10 volts AC. Yeah. Well, I could apply 15 volts AC. You're thinking in terms of the graph because you're taking the angle into account? Not really. Again, it depends. If you're applying 15 volts RMS values are basically the DC equivalent value. So then it would be the same thing. Yeah. Any other questions? Yes. Yeah, the phase angle will always stay the same, but only for that specific inductor, meaning there could be multiple inductors, multiple capacitors in a circuit. So the question being asked is, do the phase angles for inductors and capacitors always stay at plus 90 and minus 90? The answer is yes, but for each specific component, meaning if you have L1 and L2, then the phase angles between L1 and L2 might be different. But the voltage for L1 and the current for L1 will always be plus 90 difference. So when we are comparing the phase angles or drawing a phasor diagram, we have to keep in mind that the voltage and current applies only to that specific component, not in relation to other components. Yeah. Okay. So then I wanted to just do this polar to rectangular and rectangular to polar math operations. We talked about vectors, right? Magnitude and phase are with a phase angle of theta, and then rectangular coordinates, the projection of that vector on the real and the imaginary axis gives us A and B, real and imaginary parts of that exact same vector, right? So in mathematical operations, nowadays you have programmable calculators, you have online solvers. You can easily program your entire equation in there, and it'll give you an answer in one step. But if you make even a tiny mistake, tiny error in programming that equation, then your answer is going to be incorrect and you would not know it. My calculator is from the 90s, early 90s. It's like more than 30 years old. So it's not programmable. The only calculation or conversion I can do is polar to rectangular and rectangular to polar. Remember, these are the sides of a right angle triangle. That's where all of these quantities come from. Again, it's just math, but that's the basis for these representations, right? So when you perform addition and subtraction, we want the complex number to be in rectangular coordinates, and you perform multiplication and division, you would want them to be in polar coordinates. Excuse me, and I'll show you how and why. Let's say you are adding or subtracting two numbers in rectangular coordinates. Everybody, well, do people remember this? We simply add or subtract the real parts together, and you add or subtract the imaginary parts together. And so that's why it's easy or easier. It's easier in rectangular coordinates. Okay. So if you're adding or subtracting two complex numbers and they are represented using rectangular coordinates, then you simply add or subtract. You combine the real parts together and you combine the imaginary parts together. As straightforward as that. When you're multiplying or dividing in polar coordinates, let's say it's magnitude A with phase angle theta B, multiplied with another number C with the angle D. What happens here? Anyone? Magnitudes are multiplied together and phase angles are added up. And the same thing happens when you perform a division. If you have two numbers and you're dividing them, the magnitudes get divided. So magnitude A divided by magnitude C, and the phase angles get subtracted. Numerator minus the denominator. Hence, impedance from Ohm's law, impedance is V divided by I. And if both V and I are represented using complex numbers, it is the phase angle of the voltage divided by the phase angle of the current. You get theta V minus theta I. Hence, for an inductor is always plus 90. For a capacitor, it's always minus 90. All right, questions? Again, as I said, this applies to all engineering or all scientific fields. Okay, this is math. We are using that math to solve a electrical engineering problem, but the math is universal. Whether you have used it in your own fields or not, at some point you will. Okay, then impedances can be combined like resistors. If you have multiple impedances in series or multiple impedances in parallel, you can combine them exactly the same way we combine resistors. So if you have a capacitor and an inductor, let's say you have a inductor L and a capacitor C. You can represent that inductor with its equivalent impedance, and you can represent that capacitor with its equivalent impedance, ZC. Now, if the inductor and capacitor were connected in series, They are two different quantities. You cannot combine them together. But when you do AC analysis, you can represent them by their impedances. And once you represent them by their impedances, think of them as simply two resistors in series, and the ZEQ, the total equivalent impedance, is ZL plus ZC. Yes. Yes. No. Because DC is constant. The input does not change. Impedance is opposition to change of input. It's not resistance to the input, but it's opposition to change in the input quantity. And the reason it's for AC is because for AC, the input is constantly changing. It's going positive, negative, positive, negative, positive, negative. At any given point in time, the input is always changing. And hence, it is fine. For an inductor, think about it. The inductor impedance opposes change in the incoming current. So the lower the rate of change, the lower the opposition, the lower the impedance value. The faster it changes or the more it changes, the more the opposition increases, which mathematically we saw ZL, the impedance is directly proportional to the frequency, J omega L, J2 pi FL. It's directly proportional to the frequency. As the frequency increases, inductor impedance increases. As the frequency decreases, inductor impedance decreases. If F is equal to 0, impedance is 0. Frequency is 0 for a DC. For a DC, inductor behaves like a short circuit. All ties together. There are multiple levels of learning for any topic. So I try not to confuse, if you throw too many things at a time, then it's just bound to cause confusion. But again, it's all tied together. So let's take a pause, think on all of that. Let me know if you have questions. I'm just going to draw the parallel connection, but essentially it's the same. Any questions? Any questions at all? So again, impedances can be combined in series or in parallel, similar to resistors. So one final thing I want to cover is basically the next slide, where we sometimes talk in terms of reciprocal of these quantities. Again, this is not something that we'll use for problem solving, but these are terms you'll encounter in the lab. Okay, so the reciprocals for resistance is conductance, noted by uppercase G. All of them are uppercase notations. Impedance Z, impede and admit. Okay, impede and admit. Resist and conduct. And react or be susceptible. So reactance, reciprocal is susceptance. Resistance, reciprocal is conductance. Impedance, the reciprocal is admittance. When you have circuits that are connected in parallel, it is very useful to work with the reciprocals directly. So when you have the reciprocals, you can directly add up. You don't have to take the reciprocal of the reciprocals. Okay, that's where it is useful. And if you're taking the lab, you solve the pre-lab, there are equations in there that will help you solve for those. The units for admittance, conductance, and susceptance is named after the German physicist Siemens. Oftentimes, it's also used as mhos, M-H-O, simply the reverse of ohms. So depending on who's used to what, you could use Siemens, or you could use mho. But again, these are reciprocals. We will not solve problems using those specifically, but it's just something that students should be aware of. Okay. So we'll end class here today. Monday we'll do like in-class problem solving. There are 3-4 examples in this chapter. I'll go over it. The homework, there's another homework that's based on the problems, so I'll probably extend it because we won't cover the problems until Monday. So I'll extend it beyond next week. Yes. So quiz will be most likely based on chapter 5. Chapter 5, AC analysis, concepts and stuff. So probably not like big problem solving, but mostly concepts. All right. Have a good weekend. I will see you all on Monday. Oh, I won't be in my office until 2 o'clock, until after 2 o'clock. Okay. So I'll post an announcement.